Welcome to this video lesson on thinking critically and solving problems through estimation, otherwise known as when close is good enough. Close or exact, when does it matter? There are situations when precision or exactness are absolutely critical. For example, if a neurosurgeon is removing a bullet fragment that is lodged within 1/100th of a millimeter from a patient's spine, one wrong move could cause permanent paralysis of the patient. So precision is absolutely critical in that case. Or consider this. An engineer is calculating the thickness of the metal that will be used to create the lightest weight gas tank for a new high mileage car. Too thick and the car will be heavier and therefore not meet minimum federal mileage standards. Too thin and the tank could be vulnerable to puncture or stress fractures that might cause a leak or explosion. So once again, here's an example where precision or exactness is absolutely critical. Or let's say you're completing your income tax forms and you know you are subject to audit if it's not correct. Now, this is not a life or death situation, but this is also a situation where precision is necessary. Now, the IRS of the United States does allow you to round off to the nearest dollar, so they want you to be precise within a few cents. But again, you have to be very, very, very close. So precision is important. But what about times or situations where an exact amount is either unnecessary or perhaps even impossible to find exactly? So for example, you stopped for a few things at the grocery store and you know you have 20 in cash and no other money. You're supposed to pick up a gallon of milk and 2 pizzas for dinner. So as you go down the aisle to pick out the pizzas and get the milk, you recognize that maybe there are some kinds of pizzas you can't get because you don't have quite enough for that, and you also think about, well, there's tax that has to be added here as well. So you're not going to get out your calculator and find it to the exact amount, but you're going to try and do your best to make sure that when you get to the cash register, that 20 is going to cover what you're buying. Here's another. Maybe you have a low gasoline light that comes on in your car when your car is about to run out of gas. And you know you have about 40 miles before you're going to run out of gas. So you don't know exactly how far you can go before you run out of gas, but you know there's a window of time and mileage that you have to stay within, otherwise you're going to run out of gas. It doesn't matter if you've got a little more or a little less left in the tank. The key here is to get there before you run out of gas. Or let's say that the school board has allocated funding for 4 additional classrooms next year because they are expecting about 100 more students to start school next fall than started this fall. There's no way that they can know exactly how many students will come a year from now. But they've looked at the trends and they think that based on the neighborhood and the houses that may be vacant in their district, that they could have as many as 100 more students. And therefore, they have to make sure they've made arrangements for about 100 more students. Again, exactness is not going to be possible in this situation. But they need to get close enough to be sure that they have teachers and materials for all the new students who will come next fall. So if you're going to do an estimation problem, there are 2 things that are needed: rounding and then certain operations. So here's a basic definition of estimation. Arriving at an answer that is accurate enough, but most likely not exact, is called estimation. The necessary proximity of the estimate to the exact answer will depend on the situation, but is most likely indicated in the problem or by the circumstance. Take the school situation, for example. If they think they're going to have about 100 kids, if they have 105, they can spread those 5 kids out. If they have 95, well, they've got one less student in the classes. However, if they have 200, that's a major situation. So they know that they have to be accurate within a few students in order for their estimation to be close enough. Just like when you go in the grocery store. You want your estimation when you're purchasing those things to be a little under what you actually owe to make sure that you have enough money at the cash register. So depending on the situation, the approximation will be dictated by that situation. And in many problems, they'll give you some instructions on how close the estimate has to be by giving a place value to which you should round. Here's an example. To the nearest dollar, approximately how much would each person need to contribute toward a gift for a mutual friend if the gift was $49 and there are 5 friends who want to share the cost? So here in the problem, they're telling you, find it to the nearest dollar. Be accurate to the nearest dollar. And here's another. About 2,190 people are expected to attend a small arts festival this weekend. You'll be there, and you will be selling lemonade at the festival. And based on last year's sales, at least 32% of the people are expected to want lemonade. If each serving is 10.5 ounces, how much lemonade should you take? If this is your business, it's very important that you have enough on hand so you can make the most money that's possible. We'll come back and solve these 2 examples in a few minutes. But let's keep talking about what you need to be able to do in order to estimate. That next thing that you're going to need to determine is which operation or operations are needed. Now, there are some common words for operations, and by operations, I'm talking about adding, subtracting, multiplying, and dividing. These are the 4 basic numerical operations that are involved with every problem. Now, there are some basic words for each of the 4 operations of add, subtract, multiply, and divide. And so these are some of the more common words or phrases that you'll see that will indicate which one of the 4 operations you should do. So there's sum for adding, and difference for subtracting, product for multiply, and quotient for divide. Those are really the technical words for what you get. When you add, you get a sum. When you subtract, you've got a difference. When you multiply, it's a product. When you divide, it's a quotient. So if you have those words, it tells you which of the operations to use. There are some others. Adding, quite often you'll find that a problem will say, find the total. That means you need to add up things. Subtract may say reduce by. Multiply also means times. And out of can indicate that you need to divide. Here are some other common phrases. Added to, subtracted from. Of can indicate to multiply. And percent means to divide by 100, which can also be written in its fraction form, divide by 100 that way. And then multiply can mean per. So for example, if you buy 5 CDs and the cost is $8 per CD, you're going to have to multiply. So that word per can mean to multiply. Now here's the tricky part. When no direct operational hint is given, in other words, you don't see any of these specific words in the problem, you may have to try to rephrase it using one of these common words and see which one of these makes the most sense so you'll know which operation to use. You can try that operation and see if the answer makes sense. If it doesn't make sense, re-examine. Think what's a reasonable answer, how you might get that reasonable answer if you work backwards. And that can also help you to determine the appropriate operation when one of these common words is not used. In addition to understanding what operations may be involved in finding an estimate to an answer of a problem, we also have to understand about rounding. And in order to understand about rounding, we must first look at place value, or understanding the real value of a digit within a number. If you have a digit like 3, it will have different values depending on its location in a number. So you can see that there are 3's in this number at various places, and each of those 3's has a different value. We identify its value by looking at the place value of the space which it occupies. Now, when you have a decimal point in a number, it divides the number into two kinds of numbers. The numbers on the left are whole numbers, and the numbers on the right of the decimal point are fractions. And fractions just mean parts of a whole. They don't represent a whole thing. They represent part of something. Now, our instructions here are to underline the digit in the number and then identify that digit's actual value. And the first place in Part A we're asked to look at is the billions. Now, I have a table here, and you can see that billions is listed. And if I count, that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places to the left of the decimal point. And in this case, it's the number 4. Again, you can count ones, tens, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions, then billions. That 4 is not just a 4. That 4 means 4 billion. So the place value of the position that 4 occupies tells you what the 4 is worth in the number. In this case, 4 billion. Next, we look at hundred thousands. Hundred thousands, there's a 9. Counting from the left of the decimal point, just to be sure, we've got ones, tens, hundreds, thousands, 10,000s, 100,000s. So that 9, being in the 100,000s place, actually represents 900,000 in this number. And Part C asks us to find the digit in the tens place. And the tens place is just 2 digits to the left of the decimal point. In our number, that's going to be a 6, because you've got ones, then you've got tens. 6 tens has a value of 60, so that 6 means 60 in that number. In Part D, we're asked to identify the digit that's in the hundredths place. Because of the THS, we know that that number is to the right of the decimal point, and the hundredths place is 2 places to the right of the decimal point, or the 9. So that 9 actually means 9 hundredths, 0.09. And in Part E, we're asked to find the digit in the 10,000ths place, so we can count them off: tenths, hundredths, thousandths, 10,000ths. So this 5 is in the 10,000ths place, which is 4 places to the right of the decimal point. It means 5 out of 10,000, or 5 10,000ths. So once you've got the basics of place value down, you can then proceed with rounding. So there are just a couple of things that you have to remember when you're rounding. The first one is you have to find the digit in the place value you're supposed to round to. So like in example A, I have to find the digit that's in 100 millions. So this 3 is in 100 millions. Now once I've identified that number, the number which tells me about rounding is actually the number to its right. Because in this case, I want to round to the 100 millions, which is the place where the 3 is located. So I'm going to look at that 8 and decide what I should do. If the digit to the right is a 5, 6, 7, 8, or 9, you will round up by adding 1 to the digit in the desired place value. So you've got 784, and you're going to replace that 3 with a 4, and then everything that follows is going to be a 0. Now those zeros to the right of the decimal can be left off, but the zeros on the left of the decimal cannot. I know that this is right if when I read it, I end with the words 100 millions. So if I read the word, I have 784 billion 400 million. So if the digit to the right of the desired place value is one of these, a 5, 6, 7, 8, or 9, you add 1 to that place, that's how we got our 4, and then fill in with zeros until you get to the decimal point. Let's take a look at the millions place. In our number, there is a 0 in the millions place. We take a look at the digit to the right of the millions. In this case, it's a 9. Once again, we've got one of the numbers from this list, 5, 6, 7, 8, or 9, which means we need to add 1 to the place value we're supposed to be rounding to. So 784, 381, and then fill in with zeros until we get to the decimal point. And remembering the digits to the right of the decimal point can be left off if they're zeros, but those zeros on the left must be present. Again, if I read it, 784,381 million, so I know that I've rounded it to the millions. Part C, they asked me for tens. So I look at my original number. I find the digit in the tens, which is the 6. I look to the right, and if the number is not a 5, 6, 7, 8, or 9, in other words, if it's a 0, a 1, 2, 3, or a 4, I don't add 1 to my given place value. Instead, I leave the number that's in my given place value, in this case the tens, exactly as it was, but I still fill in with zeros to its right. And since I was working with the tens place, there's only one number to the right of the tens before you get to the decimal place, so I only need this 1 0. And again, zeros to the right of the decimal place can be left off. Again, in summary, if you have a 5, 6, 7, 8, or 9, you add 1. If you have a 0, 1, 2, 3, or 4, you leave the digit in the given place value alone, but fill in with zeros after it until you get to the decimal point. So in Part D, it asked me to find the hundredths. Again, in review, TH tells me it's to the right of the decimal point. In the hundredths position, I have a 9 because hundredths is 2 places past the decimal. The first place being tenths, then hundredths. I look to the digit that is to the right of 9. It's a 4, and that's one of the digits where you leave your desired place value alone and fill in with zeros as necessary. Now, because in this case we're on the right of the decimal point, it is not necessary to write those zeros. We can just leave it as 0.39 or 39 hundredths. And so the last one they've asked us to do here is a 10,000th. You look for the digit in the 10,000ths place. Tenths, hundredths, thousandths, 10,000ths. In this case, it would be the 5. To its right is an 8. That's one of the digits that tell us we need to add to our desired place value. So in this case, everything on the left of the decimal is going to stay the same. But we're going to add 1 to the 10,000ths place, giving us 3,946. That is 3,946 10,000ths. And be sure your decimal point is clear there. So once you figured out the operation and you can do the rounding, you can estimate the answer to a problem. Let's use estimation to solve some problems. To the nearest dollar, approximately how much would each person need to contribute toward a gift for a mutual friend if the gift was $49 and there are 5 friends who want to share the cost? So we've got a lot of information here. We know we want an answer to the nearest dollar. We know the cost of the gift was $49, and we know that there are 5 friends who are going to share the cost. Now, assuming that each one of them shares equally, we would use division to find this answer. However, to make it easier and to just get a quick estimate, we're going to do some rounding first. So instead of the $49, I'm going to take that and make it $50, nearest $10, divide it by the 5 friends, and I'll get an answer of 10, or $10 for each friend. If we use a calculator to find the exact amount, we can then compare our exact amount to our estimate to see if our estimate's pretty good. So if we take our calculator, take the actual numbers, 49 divided by 5, we will get 9.8. And that means that the exact or precise amount that each friend would pay is $9.80. So the estimate of $10 is a really good estimate. $9.80 is very close to $10. Here's the problem about the festival and the lemonade. About 2,190 people are expected to attend a small arts festival this weekend. You will be selling lemonade at the festival, and based on last year's sales, at least 32% of the people are expected to want lemonade. If each serving is 10.5 ounces, how much lemonade should you take? So remember, there are cases where you can never know an exact answer in advance. You just don't know how many people are going to show up. But based on last year, they've told you that about 2,190 people or so are expected to attend. And also based on last year's sales, 32% of the people are going to want to buy lemonade. So what you can do here is you can do some rounding to get a fairly good estimate. I'm going to round my 2,190 to 22, and I'm going to take my 32%. Now remember, 32% means 32 out of 100. You take 32 divided by 100, it ends up being 0.32. You might remember the shortcut for percent is you take that decimal point and move it 2 places back to the left, and that's where you get the 0.32. Now, to find the percent of something, that is the percent of people who will be buying lemonade, of means to multiply. And I'm going to round my percent to 30% because I just want to get an idea here. And rounding this number just makes the arithmetic easier. If you do this multiplication, it comes out to be 660. Now, each of those 660 people expected to buy lemonade get a serving that's 10.5 ounces. Well, that's pretty close to 11, so let's take our 660, multiply that by 11, and when you multiply that out, you get 7,260 ounces. So that's the amount of lemonade you're estimating that you're going to need so that this number of people can buy lemonade from you. Now, to find the exact number based on these values that are given in the problem, keeping in mind that you're making a prediction here anyway, you could take the 2190, multiply using your calculator times 0.32 times 10.5, and then you would get another value that would give you a good idea of how much you need, 7,358.4. So around 7360 or so. Now remember, this is not an exact value because you can't predict in advance exactly how many people are going to come. and how many people are going to want to buy lemonade. This is just based on some information you have from previous festivals. In our next example, to the nearest whole dollar, how much would you need to purchase the following items? And disregard sales tax for now. We want to find an approximate amount. Then we'll find the exact amount by using the calculator. So here's that common problem where you go into the grocery store, you have a certain amount of money, and you want to make sure that before you get up to the cash register, you have enough money to actually buy what you've picked out. So rounding to the nearest dollar, it's $3 and $4 and $4. And of course, we want to know the total of this, so we add these together and we get $11 as our estimate. Now, if we want to get the exact answer, we take out our calculator, we add these three values together, and we find out that this is $10.58. Don't forget your dollar sign. So this estimate is very close to the actual value, but remember, in an actual purchase, you would also have to add some sales tax. So you probably need to make sure you have at least $12 to make this purchase, just to be safe, so that when you get to the cash register, you're not short. Find the approximate annual gross pay for a person earning $7.75 per hour, round the pay to the nearest dollar, and assume a 40-hour work week for 50 weeks. So gross pay is the amount that an employee earns before any taxes or insurance or things like that have been taken out. We're asked to round the pay to the nearest dollar, so that's going to give us $8, which we can just write as an 8 since it's a whole number. And we're supposed to assume 40 hours a week, and that would give us $320 per week. And now we must take the amount per week and multiply that by the number of weeks, which we're to assume is 50 weeks a year. And I guess the other 2 weeks is for vacation, which is not paid. If you multiply that, you get $16,000. So the estimated amount for the person is $16,000. And that's the gross pay. That's not the net pay that the person gets to take home. Now we're going to use a calculator to find the exact amount to see what it would be. And the exact amount would mean we take the $7.75 on our calculator, we multiply it by the 40 hours, and then we multiply that by the 50 weeks. It's okay to multiply all at one time in your calculator because it's going to multiply 775 times 40 and then times 50. And that exact answer in this case is $15,500. So $15,500 is the exact amount of the gross pay, and our estimate was $16,000, so we have a very good estimate here. Now we're going to look at one of several examples of visualizing data, and there are different ways to visualize data, and this is just one of the ways, and this is actually called a pie chart or a circle graph. And in this information, we first see that this graph is representing a household budget and that there are 5 categories for this household budget. Because we have a visual of the information, we can easily tell that housing is the biggest expense of the budget every month, because we can see that that green slice for housing is much larger than the other slices. If a family's monthly income is $4,109, based on this graph, approximately how much is budgeted for food each month? So we're now interested in a specific category, and that is the category of food, which indicated by our categories here is 20%. So that purple wedge of this pie chart is for food, and it's indicated at 20%. So if we're going to estimate, we're going to do some rounding, and so we're going to take our 4109. It doesn't give us any specifics, so we'll stay as close as we can to exact. We'll multiply that by 0.20. Now, just as a reminder, 20% means 20 out of 100, which as a decimal is 0.2 or 0.20. When we do this multiplication, we'll get our estimate for the problem, and by multiplying 4,100 times 0.2, we get 820. And as a reminder, when you multiply decimals, you multiply as you normally would. We have a total of 2 here, so our decimal needs to be placed with 2 digits past the decimal. So that gives us the 820. Now, 82,000 would not make sense, nor would 8,200, because that would be more than the entire amount that they bring home. So this reasonable estimate of 820 makes more sense. Now, if we want to find the exact amount, we can take the 4,109. We can multiply that times the 0.20, and you can do it by hand or you can use the calculator, and you'll get 821.80. So put these dollar signs here to indicate that these are dollar amounts, and you'll notice that our estimate, or our approximate answer here of 820, is really close to our exact answer of 821.80. So we found a really good estimate for the amount that this particular family budgets for food every month. Here we have another example of a graph that can help us to visualize our data, and in this case we're actually going to create a math model. We have a bar graph here, and this bar graph shows the number of students, here's your students, that were enrolled in a nursing program at a large health sciences university, and we know that number for some periods of time every 5 years, starting in 1990 all the way up to 2010. So we're asked to find the average yearly increase in the number of students in the program. But we're also going to be asked to create a model. We're going to create a mathematical model that estimates the enrollment in the program X years after 1990. So any number of years after 1990. Not just every 5 years, but any number of years after 1990. And we're going to use this model to predict the enrollment out here at 2015. So if there were another bar added out here at 2015, we want to know what the height of that bar should be 5 years later, after 2010. So the first thing we have to find is the average yearly increase. So in other words, how many more students are entering the program every year since 1990? Now, there are a number of ways to do this, but we're going to just take the number of students the first year were given and the number of students the last year were given. And from that, we're going to find the additional number of students per year that enrolled in this program. Well, we first need to look at the increase. So it's obviously gone up from 606 to 2488. If we subtract these two amounts, we find the increase. And we're looking for the yearly increase. So it's increased by 1,882. But that's not for a year. That's for the period from 1990 all the way out to 2010. So if we subtract those two amounts, that is 2010 minus 1990, we get that that's a 20-year period. So if we want to have a denominator of 1, because this is students and this is years, and they want us to find it for yearly, that is per 1 year, we just divide that number out and we get 94.1. And so we're going to call that at 94 students a year. So 94 students have been added to the enrollment every year starting after 1990. So in 1991, there were 94 students more. And in 1992, there were 2 times 94 students more. So every single year after 1990, on average, the program added 94 additional students. So to create a model that will describe this mathematically, where X is the number of years after 1990, we just go back to what we know. We'll use E for enrollment. We know that we started at 606 students. And we know that we're adding 94 students for every year. And we're going to let X mean years. So every year past 1990, we have an additional 94 students. So that's 94 students per year, or 94 times X. So our original amount, 1606, and 94 for every year after 1990. Now that helps us to find 2015 because we know how many years after 1990 2015 is. You can just subtract to find that. 2015 minus 1990 is actually 25 years. So to find our enrollment, and this is to sort of estimate the enrollment in 2015 because we've done some rounding and we don't know exactly that this is what's going to happen. We just say our enrollment is 606 plus 94 times 25, and I'll use the parentheses to indicate the multiplication. Now, according to the order of operations, we always multiply before we add. And if you have a scientific calculator, a graphing calculator, like's required in this course, it's going to know to do the multiplication first and then do the addition. If not, if you've just got a 4-function calculator at this point, you need to remember order of operations, multiplication comes before addition. So we have to multiply the 94 times 25 and then add it to the 606. And when we do that, we'll get 2956. So 2,956 students is what is expected in 2015. So this bar would be at 2,956. Sometimes when visualizing data, we'll be given some information and we want to just come up with a basic sketch of the graph, sort of describing what's going on, and we're not going to worry too much about exactness. A light has been turned on for several hours and has heated to a maximum temperature of 260 degrees. And that would be Fahrenheit, so I'll put a little F there for Fahrenheit. Then the light is turned off. Sketch a graph of the temperature of the bulb over several hours after the light has been turned off. Now you have to be careful here. Your first instinct, of course, it would be correct, and that is that it starts out at 260 degrees. And you might just want to draw a graph that looks like this because you know it's going to get cooler and cooler. But be careful. Think about it for a minute. Is the temperature of the bulb ever going to get to 0? Or is it ever going to be negative? Would it even be 32 degrees, which is freezing? If this light bulb is inside a house, that's just never going to happen. It's going to start at the 260, and it is going to cool off. And it's probably going to cool off pretty rapidly, but then it's going to level off. And the reason it's going to level off is that it can only get so low, and the lowest it can get is actually the room temperature, whatever the temperature is of the surrounding environment. So let's just say that it's 78 degrees in the house, and so over time it's going to settle at a temperature of 78 degrees. So it's got sort of a pretty fast decline followed by just a steady temperature of 78 degrees. Now, of course, if the light's turned back on, the graph's going to go back up as the temperature of the bulb heats up again. So this is just a basic sketch of what this data would look like. As a hurricane approached, the amount of rain per hour rapidly increased, then leveled off, but continued to pour for several hours at a steady rate. Show the amount of rain falling per hour beginning with as the hurricane approached and continuing for several hours. So once again, we've got time along this horizontal axis, and it's in hours. And here we've got rainfall in inches. And so as the hurricane approaches, the rain is increasing rapidly. So let's say that there was a little bit of rain before it started to approach, and it really increases. And as the hurricane stays in the area for a while, it levels off. Again, it's just a basic sketch. We know there's a rapid increase followed by leveling off. Then, of course, if we go enough hours out, you're going to see a decline in that rain. But again, just a basic idea of what is happening here. Rapid increase followed by a leveling off.